Thank you. This is joint work with Toby Cathcart and Luke Ong from the University of Oxford. And the idea of this work is to take the notion of constrained horn clause, which is a class of formulas in first-order logic, and generalize it into higher-order logic, and see if we can make that definition work to support automated program verification. The reason that we want to do this is that over the last 5 years or so, constrained horn clauses have become quite an important notion in automated program verification, particularly in first-order program verification. So let me start by talking a bit about first-order constrained horn clauses. So one way to motivate constrained horn clauses in general is to talk about invariants. And obviously invariants are a very important tool in verification. And there are many different kinds of invariants that have been developed, each sort of specialized to the types of programs or the properties that you want to verify. For example, if we model our program as a transition system, then we know we don't have to look for any old invariant. It suffices, for example, to prove safety, to find a so-called inductive invariant, that is, a property that holds of the initial states, is preserved by the transition relation, and implies the safety property. If we distinguish more structure in the model of the program, for example, if we distinguish procedure calls and returns, then we typically want a more structured kind of invariant. For example, procedure summaries are a very often used one. And one thing that these notions of invariant have in common, and many other notions of invariant besides, is that they can both be described as the solution to certain systems of constrained horn clauses. This was the observation of Rybolchenko and his colleagues in, I think, a PLDI paper of 2012. And in 2014, we have this sort of survey paper by Nikolai Björner and his colleagues, which tries to justify the following claim. They claim that first-order constrained horn clauses provide a suitable basis for automatic program verification. So some of the bullet points on this slide express some of their justifications, but I just want to draw your attention to the middle bullet, which describes the good algorithmic properties. So one is that although satisfiability for this class of formulas is typically undecidable, they do have the least model property, which means that if you have a system of clauses that is satisfiable, then in fact there'll be a least satisfying assignment, where least means in the subset order, the size of relations. But moreover, another good property that they have is that much of the technology that's been developed for efficient symbolic model checking carries over to constrained horn clause solving. So technologies like predicate abstraction, PDR, IC3, and lazy annotation. So as a result, there are already many very efficient solvers for first-order constrained horn clauses. Now, we're interested in the automatic verification of higher-order programs, for example, functional programs. And for higher-order programs, sometimes you want to write invariants or find invariants that talk about functions directly, in which case first-order logic isn't necessarily the best setting in which to do that, and you prefer to do it in higher-order logic. Well, so constrained horn clauses, since they're a class of first-order formulas, aren't going to cut it. But obviously, there's a kind of natural way in which you imagine you could lift the definition of constrained horn into higher-order logic. And this is the starting point for our work. So the generalization that you get, we call higher-order constrained horn clauses. And with analogy to the first-order case, we ask, to what extent can they be used for higher-order program verification? So in this paper, we focus on the algorithmic properties part. So the bad news is that there is no least model property for the higher-order version, but we show that to each instance of the satisfiability problem for this class, we can associate another kind of satisfiability problem, a more sort of non-standard one. We call it the monotone problem. And this problem does have the least model property. And furthermore, we can build an efficient solver that uses all the technology that's already known from higher order program verification, in this case, refinement type inference. And then we show that, in fact, consideration of this other non-standard problem, there's no loss in doing that, because each instance of this satisfiability problem that we started with is related to the instance of this non-standard problem that we associate with it by being equisatisfiable, equisolvable. So let's look at what these things look like with an example and hopefully see how they're related to higher order program verification. So in the top left, you can see a functional program. It defines two functions, add and iter. Iter takes a function, a binary function on integers as its first argument, and it iterates it over the other two. Then in the end, the program asserts something about their combination. And let's say we're interested in verifying this program. It's a recursive program, so we're going to want to find some kind of invariant. But what's a good kind of invariant for a functional program? It's not usually useful to model a functional program as a flat, unstructured transition system, so it's probably not going to be an inductive invariant in that sense. Rather, we would model our functional program maybe as a collection of mutually recursive function definitions, in which case I suggest that perhaps a good notion of invariant is a collection of function summaries. So for each function in the program, this invariant will have a summary of that function, which is a relation that over-approximates the input-output graph of the function. So the invariant will have, corresponding to add, a relation that over-approximates its behavior called, let's say, add r. Similarly for iter. And add r is going to be an over-approximation of the graph of add. So it's going to be some set of triples that at least contains x, y, and z whenever they're related by z being equal to x plus y. So if we can find a set of triples that satisfies that condition, it will be indeed an over-approximation of the graph of addition. And similarly, we can write a couple of constraints that describe what it means to over-approximate the graph of this iter function. But this iter function was higher order, right? So its graph contains points which are themselves functions. And a natural way to model that is to make the relational over-approximation itself a higher order relation. And this is why we start to enter higher order logic. So if I can find two particular relations, add r and iter r, that satisfy the first three clauses, then I will have an invariant. They will constitute an invariant in the sense that I described. If they furthermore satisfy the fourth clause, then it will be an invariant strong enough to verify the safety of this program. So if we can accept that a collection of function summaries, in the sense that I described, is a reasonable notion of invariant for a functional program described as a collection of functions, then we are led to a description of such invariants in higher order logic, and moreover, in this fragment, higher order constrained horn clauses. So I'm not going to give a formal definition, but I hope you can recognize the constrained horn shape of these clauses. So if you're not familiar with the constrained part, it comes from, for example, constraint logic programming, because these clauses are typically going to be formulated over some background theories, so they may contain atoms from the background theories. But importantly, the predicates that you're solving for, like add and iter, what was add and r and iter before, must be restricted into horn-like positions. So they're constrained horn clauses, but they have these higher order twists because they're in higher order logic. For example, we have higher order unknown relations. As a result, we end up with quantification also at higher order. So the quantification was implicit in the previous slides, but of course it looks like that. And we also end up with things like literals that are headed by variables. So these are twists that are not there in the first order case. And these twists make the model theory a bit more interesting than in the first order case. So in particular, they preclude this least model property. So we interpret formulas according to the standard semantics of higher order logic, which means that we allow consideration of all possible set theoretic functions when it comes to assigning the meaning for functions, although everything is simply typed. And the consequence is that we have this theorem. So for this particular single clause, it's a system that has two minimal models, two distinct minimal models, and so therefore no least model. Now, in both first order and higher order constrained horn clauses, it's not allowed to have negation of the unknown predicate symbols in the clause bodies. And in the first order case, it's this restriction that is allowing you to see that the clause body is a monotone function semantically of the unknown predicate symbols. And it's this monotonicity in the end that gives you the least model property. But in the higher order case, that's not true. So if we look at this clause body in the higher order case, so x, the subterm xq, is this a monotone function of q? Well, it entirely depends on what gets assigned to x. If x gets assigned a monotone function, then indeed xq will represent a monotone function of q. But we have to consider all x. It's quantified with for all. And we're considering the whole set theoretic universe. So we have to consider that sometimes x gets assigned a function which is not monotone. And so we don't have monotonicity in general. Now, this is really the only problem. So there's a kind of obvious solution, right? So if we just exclude from the universe all the non-monotone relations, then we're good. We will recover the least model property. It's quite a big change to make because we're changing the semantics of higher order logic in order to do that. So when we do that, we're saying that for all x really means for all monotone relations x, or monotone functions x. And solutions now become assignments of monotone relations to the unknown predicate symbols. And this, so if we consider this monotone universe, we get to state an alternative kind of satisfiability problem, which we call the monotone problem. So the monotone problem says, is there a monotone valuation that satisfies the system in the monotone semantics with respect to this different definition of truth that only considers monotone things? And the good thing is that for this problem, that we have this least models property. But we're not happy about it because it's really a very strange kind of problem. We've made this arbitrary seeming restriction, whereas in the original problem, it was just a standard satisfiability problem about some class of formulas in higher order logic. But now things are a bit more complicated. Ideally, what we'd want is to have the best of both worlds. We want to specify our problems in the standard semantics because it's very clear what the meaning is, but then solve those problems algorithmically using the monotone semantics because we've got a least model that we can try and approximate algorithmically. And monotone relations, anyway, are better behaved computationally. And in fact, that's one of the main results of the paper. We have this theorem that says if H is a system of higher order constrained horn clauses, then H is satisfiable in the standard semantics if and only if it's satisfiable in the monotone semantics. So that latter part means that there is an assignment of relations where all the relations are monotone. In fact, I should say hereditarily monotone. And it makes the system true under this monotone semantics. So the key construction in the proof is a pair of families of Galois connections that relate the class of all monotone relations and all ordinary relations at every given relational sort row. And because models, that is, assignments of relations to the unknown predicate symbols, their main constituent are relations, we can use these adjoints to map between valuations from in the monotone world and valuations in the standard world. And we can show that the upper adjoints in particular will preserve the quality of being a solution. So this theorem allows us to solve this our original satisfiability problem concerning higher order horn clauses by solving this non-standard problem in which everything's monotone. And the second half of the paper is really about how we go about doing that. And in particular, we were keen to show that, just like in the first order case, solving these systems of clauses is somehow a natural extension or evolution of the work that's already gone on in verification. So for us, an important point in the space of higher order program verification is refinement types. And so that's what we adapted in order to solve systems of higher order constrained horn clauses. So we designed a type system, a refinement type system, that would approximate the monotone semantics. So for us, refinement types came in 3 flavors. So either they are just the unrefined type int, or in general, whatever your sort of individuals is, depending on what your background theory is. The type bool, refined by a first-order formula from the background theory, or the dependent product. And the key idea of this refinement type system can best be seen when we consider a judgment that has this shape. So we have some type environment gamma. We have a goal formula G. A goal formula is just the body of a clause. And you have this type bool refined by a first-order constraint phi. And the important thing to note is that this constraint formula phi is a simple object. It's a first-order formula, comes from the background theory, which is something like quantifier-free integer linear arithmetic, decidable. But the formula G is a complicated thing. It's in higher order logic, and it contains these unknown predicate symbols that you're trying to solve for. Now, what the type system is telling you is when you can conclude a judgment like this, then you can deduce that this simple formula phi is in fact a good approximation to the truth of the complicated formula G, in the sense that if you have a valuation that refutes phi, then it will certainly also refute G. So this type system allows us to set up a kind of sound approach for solving systems of higher order clauses. We have a theorem that says that if you can find a type environment, gamma, which types a system of clauses, then in fact this type environment is a representation of a model of that system. And we know from the work in refinement type inference that finding a type environment, in other words, typeability, actually reduces to first order constrained horn clause solving. If you remember at the start, as I said, there are many efficient first order constrained horn clause solvers already. So taken as a whole, this seems like a reasonable approach for trying to solve the higher order case. So we tested that by writing an implementation that encodes this methodology. So it's called Horus, and it's available from GitHub. And we ran it on a large subset of the benchmarks that come from this paper at the bottom by Kobayashi, Sato, and Ono. This is an influential paper in higher order model checking. We took all the verification instances from that paper and converted them by hand into higher order horn clause problems, and then gave them to our tool, which reduces these higher order constrained horn clause problems to first order constrained horn clause problems using refinement type inference. And we found that actually it was very competitive. So on all but one of the benchmarks, it was able to solve them, and it only took a few milliseconds. So the benchmarks are generally quite small, just 1 or 2 functions, but they encode interesting verification problems, which is why they were in this paper. So one of the benchmarks was satisfiable, but we couldn't find a model automatically. That's because the type system, which is our method for solving, is in the end conservative. So there's an incompleteness there. This brings me neatly onto the future work. So one item of future work is to try and look at other alternative methods for solving these higher order constrained horn clause problems that hopefully don't have the same incompleteness issues, maybe something that's relatively complete. To that end, we're looking into defunctionalization, which obviously is a program transformation, but can be repurposed because horn clauses are, of course, sort of the computational clauses of logic. We're interested in looking at the expressive power especially with respect to higher-order program verification. And higher-order program verification differs a little bit from first-order program verification because you're often interested in, does a function satisfy a property of functions, rather than just does a complete program satisfy a ground-type property. And finally, we're interested in whether there are new applications to program verification, program analysis that can come about with this sort of expressive language of constraints. So for example, there are many program analyses that are described as performing some recursive pass over the syntax of a program and emitting constraints that are then solved. But typically, these constraints will be first-order constraints. Now we've got a language of higher-order constraints, so can we do better? I don't know, because there'll be trade-offs involved. I mean, one concrete example would be if you look at refinement type inference for functional programs, there the idea is that you're refining a type by a predicate. But perhaps we want to do it more compositionally. We might want to refine a type constructor. A type constructor is a function on types, so it should be refined by a function on predicates, which is just a higher-order relation. So can we do a version of refinement type inference, which is compositional in this sense, and where inference reduces maybe to higher-order constrained Hornclaw solving rather than first-order? Thank you.
So we got a few online questions, but audience, feel free to raise your hand if you need a question, ask questions. So the first online question, is the technique scalable for large programs where you are free to define what large means? How scalable it is?
Yeah, so I mean, it's obviously an excellent question, and it's one that we just can't answer at the moment because it's very, very early stage in the work. So we've only had this prototype solver, which you can think of as kind of feasibility study, really. So scaling to larger programs is something we hope to do in the future.
So I have a question. So essentially, you take the problem of higher order constrained horn clauses and you reduce it to the first order using refinement types. So could you comment how your work relates to the work of Jala, Majumdar, and Rybalichenko on taking the verification of higher order programs to the verification of first order programs using refinement types? It sounds very related.
Yeah, it definitely is related. So I mean that. Sorry, could you just repeat which paper precisely did you say?
Actually, I have it right here on the phone. So it's essentially called HMC, verifying functional programs.
Oh yeah, sure. Okay, so it's very related indeed. So they start with a higher order verification problem, and they reduce it to a first order verification problem. So we're doing a similar thing, but with just on the logical side. So we're reducing this logical problem to another logical problem. But it's exactly the same idea.
So even for, can you hear me? Yeah, even for first-order programs, I was wondering whether if you wanted to synthesize ghost code and ghost code or ghost functions which will help prove a program correct, I wonder if that would be phrasable as a higher-order logic synthesis problem using horn clauses.
Yes, I mean, I don't know this domain very well, but I think it sounds very plausible that that would be the case. So synthesizing, I suppose, programs in general is something that we're very keen to look at with respect to these clauses, but it's not something that we know much about at the moment.
All right. Let's thank the speaker again.